This is Network Analyst creating network data sets, the presentation you're attending, and I believe the last presentation of the day, so thank you guys for coming out. My name is Patrick Stevens. I'm a product engineer on the Network Analyst team. This is my coworker, Alan Hatakiyama. He's also a product engineer on the Network Analyst team. Before I get to the agenda of the presentation, I wanted to mention that this presentation is going to be done in ArcMap. And that's because we aren't done with the equivalency. We aren't completely done getting all the functionality from ArcMap into Pro as far as network data sets are concerned. So a lot of it is done, but not all of it. And we don't want to start presenting it without the complete story, so you have to go back and forth to do everything. So we'll focus on ArcMap and run through it, this presentation that way. And I see you're happy about it.
No, this is the reason why I came, because I was so excited to see what was happening with network analysis in Pro.
Yeah. So as you can see these slides, you can do a lot with network data sets. You can edit the attributes, you can edit the sources and do the connectivity, and we'll talk about what all this stuff means as we go forward. You can set up historical traffic. What you can't do currently is create a network data set from scratch, like from the very zero basis. And so once you've got a network data set, you can work with it in Pro, but not quite yet. So until we have the whole story, we're going to focus on ArcMap. So hopefully we'll get it done by the next release, if we're lucky. We'll see, but no promises. Okay, so our agenda for today, creating network data sets. We're going to start off with seeing whether or not you even need to create a network data set. There's other options and things available for you that maybe you can get your work done without having to create and manage your own network data set. So we'll discuss that. And then we'll go over what kind of data you use that might work within a network data set and some of the functionality offered by network data sets, including turns and signposts and traffic and attributes and travel modes and a few other different things. And we'll pepper some demos throughout. So the first question that I mentioned is, do you need to create your own network data set? Now there are routing services. Each of the solvers that Network Analyst uses are available as web services. And if this works for you and you don't mind using credits, because that's what the services charge, then maybe you don't need to have your own local data. Because network data sets take work to manage and they take work to build, and you need to have some specialized data. And we offer worldwide historical traffic and all the functionality that goes into a complicated, well-built network data set that you can solve your routes against. And so maybe that would be a good option for you. Another option is purchasing an already built network data set. You can do this with StreetMap Premium, which is they have a booth next to the Network Analyst booth downstairs. And it's a compressed file geodatabase that's already built, has a ton of attributes and restrictions and costs that you can use for a network, and you can do your routing that way. If you want to buy a network data set, but you need to add some of your own streets to it, for example, some oil roads or a new subdivision on a city, then there's a product called StreetMap Premium Custom Roads, and that way it's an editable network data set that you can use. So that can be a good option. Another option, if you're starting from scratch, is OpenStreetMap. So OpenStreetMap is crowdsourced data, so you have different amounts of quality depending on where in the world you are and how well the crowd has sourced the data. And also remember that this OpenStreetMap data isn't built for routing. So you can make a network data set out of it, but it might have some strange attribution and strange kind of connectivity depending on how well the data was put together. But if you have nothing to work with to get started and don't have credits, then this could be a good starting point. You can also create a network data set from another network data set. So if you already have a network data set that's been built, you can export that as a template and use that to build another network data set. So create template from your network data set, create network data set from template are the two tools I want you to notice off of this one. The important thing with these two tools is that the schema of the data has to match when you build it. So this is good, for example, if you have multiple cities you're trying to build network data sets for, so it's disparate data that you all want in one routable network, then you can use the templates to build it. It's very helpful. But you get through all this and you say, no, I still need to create my own network data set out of my own street data. And so to do that, it's important to understand your data going in. So of course you want to look at the format. Is it two-dimensional or three-dimensional, for example? See how the geometry lines up. Are the lines connected well? Are they overlapping lines well attributed? And speaking of the attributes, read the documentation for your data. As we'll see when Alan goes through creating a network data set, some of the fields on the data can have weird cryptic names like CFCC. And so read the data documentation, see what these things mean, and they might be important to you, and you might be able to use it with your network. Excuse me. Then think about what type of analysis you want to do. So are you doing just simple routing? And if you're using routing, is it enough that you don't incorporate traffic? Or is time of day important for travel and you need to have traffic? So you can find out if your data even supports the type of analysis you want to do before you go in, as that bullet says. And so the basis of a network data set is this sources of the network data set. You see on the right-hand side, there's a geodatabase with a feature data set, and inside there is where the network data set lives. It's called streets_ND with a little icon. And this network data set is built off of source features. You have to have your streets, for example. And most importantly, you need at least one set of line features. We mentioned streets because that's the most common one, but people build indoor networks out of hallways, sidewalk networks, or all sorts of whatever you're trying to route upon. But generally, streets, and you need at least one set of line features. Point features exist when you build your network. We automatically create junctions. That's points where all these networks, or all the edges, the lines connect. So that could be intersections, for example. And sometimes people have their own intersections with their own information that they build into the network, and you can do that with point features. There are turn features. This is about transitions between edges. It's not enough just that the lines are connected. You have to travel from one edge to the other. And I'll talk pretty extensively about turns in this presentation. And there's some other additional sources that can be involved in networks. There's tables for traffic. There's tables and feature classes that can be involved in generating directions for your routes. There's also some very common fields that you can have in street data, and I want to cover a few as we go in. One being elevation. So if you have two-dimensional data, you can do three-dimensional routing with building levels or overpasses and underpasses. And so elevation fields can help establish this connectivity in 3 dimensions. You have one-way fields, which can tell you whether or not this street is a one-way road, which is important, that you can't travel in both directions. And I'll show you how we configure that in a little bit. You see length, travel time, and speed are examples of fields that you can use to build costs on your network. I'll tell you what a cost is a little bit later on, but in general, it's the thing you're trying to solve against. Am I solving for the shortest time? Am I solving for the shortest distance? You can build that out of some of the fields on your data. Hierarchy ranks the streets by importance. So freeways, highways, can be a little bit more important than maybe alleys, and so the solvers can use this information to help minimize your routes. And there's a couple common fields for generating directions, including road class and a street name or address data field that Alan will go over in a minute. So that was sources and some of the fields that could be on your sources. And the next important thing to realize is connectivity within your network. Lines are just lines. They're just lines on a map. They don't know about each other. They don't have anything to do with each other. And one of the things that a network data set does is it establishes connectivity between the lines. How are they related to one another? Do they touch, and can you travel between them? It's important to establish a vertex where these lines cross in order to make sure that these lines are connected. If you have a vertex on a line, then you can have a connectivity policy of any vertex. And that way, wherever lines cross, but they both have a vertex, which a point inside the line, then you can travel between these lines. If you set up endpoint connectivity, then the lines can only be connected where they end. So in order to create these vertexes so that you can have, coincident points so that you can establish transitions between the lines, you can either build a topology, which is possible, a little complicated, and you can set up some pretty interesting rules to set up your topology, or you can use the integrate tool, which is what we recommend, which is the geoprocessing tool on the right here. And what the integrate tool does 2 things. First, it'll put a vertex where lines cross, so everywhere you have lines crossing, it'll add a vertex, and then you can establish your connectivity that way. And maybe more importantly, it'll snap features together that look like they're connected but aren't quite connected. Like you see 2 lines and it looks like it's connected, but for some reason you can't route between them. And you zoom way in and you realize that the lines are just not quite touching. With the integrate, you can establish a distance to snap lines together, like less than a meter or something like that. If it's that close, then assume that they're connected. I mentioned elevation fields a couple minutes ago. Now this is to establish 3-dimensional connectivity in 2-dimensional data. So we think of them as levels. So you'll see Alan mentioned Z-level fields, and that's an integer field that you put on your data that says what level are these fields at. A simple example is a street that is just on the road or on the ground and doesn't pass over anything, nothing passes over it. You give it an integer of 0, and that's the level that these streets are at. But if you have, say, 4 streets that connect They look like they connect, and if you were routing on this, you'd be able to drive from one to the other, but this is really an overpass. What you would do with your elevation fields is add the integers that match for the roads that connect. So the green roads each get an integer of 1, so we know that those connect as an overpass, and the orange ones got an integer of 0, so we know that those are connected, but the ones and the zeros don't connect. So it's as if you built 3D data with two-dimensional fields. So we talked about sources, and we talked about connectivity, and now we'll discuss attributes before moving on to the demo. This is a picture of the network dataset properties, and if you see the usage column, that is the attribute types that are available on network dataset. There's costs, which I'll cover first, restrictions, hierarchy, and descriptors, and I'll go over all 4 of those types of network attributes now. First is cost. Now, I said this is what you minimize along your network. Are we finding the shortest distance? Then we're going to accumulate all the distances as we travel out and find the least distance from one point to another. One interesting thing about costs is that they're apportioned. If you're going along a 1,000-meter edge and you only travel 60% along the meter, then you only accumulate 600 meters of distance. Same thing with the time and the drive time or whatever energy or cost in dollars or however you've set up your cost values on your network. So that's cost attributes. Then there's restriction attributes. Now these are a true, false, on, off. Is this element restricted thing? The examples here are one-way streets. Is it restricted in one direction or the other? Prohibited turns. Can I not make a left turn between these two edges? Height restrictions, which we'll cover pretty extensively as we go forward. And as I mentioned, costs are apportioned. Restrictions are true or false. Is this element restricted or not? The most common example of restrictions is probably that of a one-way restriction. If there's a street, State Street, I'm using again, and it is traversable in both directions, then you can have a one-way field with nothing in it, and Alan will show you how that will convert to mean that you can travel in both directions. But if you want to establish that it's only traversable in one direction, then we need a value in a field that can align with information about this edge, this street, so that we know which way to travel on it. And the way we do that is through what's called digitized direction. When you draw a line in, click, 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 that's the digitized direction. The first point, the second point, the third point. And now it's in that direction, so that's from to. And so in your one-way field, you can use FT, for example, or whatever you want to do to indicate that this road is traversable in the from to direction. And conversely, if it's only traversable in the to from direction, then you can set up a TF in your field, for example. And then when you're routing, you can see that this is only traversable in the to the from direction of how it was digitized. So that was costs and restrictions, and now descriptor attributes. Now these make sense. It's called a descriptor. What it does is it describes a network element. It describes an edge or a junction or a turn. And it is a description for the entire length of that element. Is this a dirt road? What type of intersection is it? Is there a certain width on this network element? Is there a certain height? That's the examples here. And then you can use these descriptors to build restrictions. Is my vehicle too tall to fit within the height limit of this road? Descriptors are also used for generating directions, if you're generating directions for your route. I mentioned the RoadClass field. That's an integer field, see 1 through 5 as an example here. Identifies different types of roads. So when travel happens on these roads and directions are generated, then it will give you the right thing. It'll say take the roundabout because we know that this road class is a RoadClass 5. So that was costs, restrictions, descriptors, and now hierarchy is the 4th type of attribute. Hierarchy attribute helps with long-distance routing. If you're routing all the way across the United States, for example, from Los Angeles to Maine, you don't want to search every single street in the entire country to make sure you found the exact right route. As the search goes out, you can start to filter away some of the smaller level roads as you move up towards freeways. And so you establish a hierarchy attribute that says which roads are more important or ranked higher. And then the algorithms can use that to help routing. I'll turn it over to Alan now for the first demo, and he's going to show you working with Tiger data.
All right, thank you, Patrick. I've downloaded the city and county of San Francisco Tiger data, and I'd like to create a network data set on it to perform routing for vehicles. So as Patrick mentions, the first thing I want to do is to examine what this data contains. So I've added it to ArcMap. And I'm going to open up the attribute table and take a look at what attributes are present. First field I see is the TLID field. What does that mean? So in order to answer that question, I need to open up the documentation, and I look up, and it says it's Tiger line ID. Basically, it's a unique identifier for each street in the Tiger database. Okay, not that interesting for my network data set. Let's look at some other fields. We have F node and T node fields. Again, looking at the documentation, these are a unique identifier for the node number for each end of the street. So far, nothing for my network data set. Aha! Length field. I could use this for my cost attributes. But what units are they in? Again, refer to the documentation, and I could see that this is actually the length of each street in miles. So I'll make a note that I have a length field, and it has distance in miles, and I'll make that for my network data set. What else does this data have? It has some string fields here. FE dir P, FE name, FE type, FE dir S. These are the names of each street, and it's segmented for each component of the street. The dir P is the prefix direction, like north or south. FE name is the base name. FE type is the type of road, for example, like avenue, road, or street. And FE dir S is the suffix direction in case the north or south identifier is at the end of the street, end of the name as opposed to at the beginning. I can use these fields for my driving direction settings so that when I generate driving directions, the street name is used within it. Next field is CFCC. What does that mean? Well, if I look at the documentation, it says Census Feature Class Code. If I read some more, it actually tells you what type of feature for each of these streets are in the Tiger database. The A indicates that it's a street, 4 indicates that it's a residential street, and the 1 represents that it's an undivided highway. I could actually use this information to determine the RoadClass attribute for generating driving directions, because there's codes for roundabouts and ramps and highways. So I'll make use of this. The next fields are integer fields that represent the address ranges. Might be useful for if I'm setting up a locator. This is beyond the scope of this presentation. Similarly with the zip code fields. There's some census provided fields, not useful for the network data set. We also have some CFCC fields that are the generic version of the CFCC field that I talked about earlier. CFCC1 is the broad category, and CFCC2 is the intermediate category. If you'll notice that in the map, when I was looking at the data, I've symbolized based on the CFCC2 field. I could also use the CFCC2 field to generate speed information. And then finally, we have a source field, and that's basically how the census sourced the data. So I've taken a look at all the fields that's been provided in the data, but I also want to know what information is not in the data that I need to add. Well, first of all, as I kind of alluded to with the CFCC2 field, not every street travels the same speed. So I'm going to leverage the CFCC2 field to make a speed field. So let me go and create a new field. And I'm going to create a field called speed of type short integer. And then I go over here and I want to calculate this field using an expression that I've written previously. So what this is going to do is it's going to read from the CFCC2 field, and it's going to assign a speed value based on that value. So A1s are 65 miles per hour, A2s are 45, A3s are 35, and so on and so forth. Click on OK. It's going to read information from the CFCC2 field and populate the speed field with the appropriate speed values. What else is missing from this data? Well, in San Francisco, we know there's a lot of one-way streets. Not every street can be traveled in both directions. So I'm going to have to create a new field for that. So I'm going to add a field. I'm going to call it one-way. And it's going to be of type text. And it's going to be of length 2. And I'm going to fill this in using the information, the same notation that Patrick talked about, FT and TF for each direction of travel. And finally, what else is missing from the data? Well, we know that in San Francisco, not every street is on the on the level ground. Some fly over others, especially for freeways. So I got to create some elevation fields. So I'm going to create a field called FZLev for the Z level on the from end of the road. And then I'm going to make it a short integer. And likely I'm going to create another field called TZLev, also a short integer for the to end of the road. So let's zoom in on interchange. This is the interchange between US 101 and Interstate 280. And I want to code the one-way information and the elevation information for one of these ramps. So to do this, let me start an edit session. And let me highlight all these segments for the ramp that I like to code. So what do I know about this ramp feature? This ramp feature travels from this end here to this end up here. It's a one-way street from this end on the bottom to this end on top. So I'm going to open up the attribute editor, click on the top level, which lets me edit them all at once, and I want to fill in a one-way field. But what value should I fill in, FT or TF? Well, that depends on the digitized direction. Well, how do I figure out what the digitized direction should be? Let's change the symbology of this orange symbol and use the symbol of arrow right at middle. If I click OK, it actually shows me the digitized direction. I notice that's digitized opposite the direction that I want to travel. So now I know I could fill this in with TF. What else do I know about this ramp? It actually flies over all these other streets. It's not connected to the streets except at the very ends of the ramp. So because it's elevated, I want to make these values 1. FZLev and TZLev, both 1. So that means that none of these are connected to any of these streets except over here. So this segment right over here is connected at ground level, level 0. It's the from end, it's the arrow pointing away from it. So let me change that to 0. And then this segment down here, it's the to end that's at ground level. So let me change TZLev to 0. Okay. Save my edits and stop editing. So let's create a network dataset from this data. So let me right-click on the shapefile, click on New Network Dataset, give my network dataset a name, click Next. Do I want to model turns in the network dataset? Probably later, so I'll keep it as yes. That way I could get global turns. Connectivity. Let's open the connectivity dialog. I know that the streets are connected at just the endpoints, so I'm going to leave the policy to endpoint. Click Next. I want to use the elevation fields I set up so that not only does it just connect only at endpoints, but only at those matching elevation values. It's automatically selected the FZLev and TZLev fields I've set up. Click Next. It's also read all the other fields in the feature class and detected the length field. But it doesn't know what units they're in, so let me specify that now. That's in miles. It also detected the one-way field and set up evaluator expressions that use the FT and TF notations. So in the from to direction, TF is restricted. And likewise in the to from direction, FT is restricted. So that's set up for me already. RoadClass attribute has automatically been detected from the CFCC field. If I open this up, it's reading from the CFCC. Anything starting with A1 is a highway. A60s and A63s are ramps. There are several codes for ferries, and the roundabouts are A62s, so that's already set up for me. But I want to model travel time in minutes for a vehicle, so let me create a new attribute. Name it minutes. It automatically set up minutes, and I want to use this as my default attribute. I have to tell ArcMap what the minutes attribute is, how it's to be evaluated. So I want to set this up to be reading from fields. Click on the evaluator properties, and I'm going to create a mathematical expression that takes the length of the feature and divide it by the speed. Length divided by speed is travel time. But the length is in miles and the speed is in miles per hour. But I want this to be evaluated in minutes, so let me multiply by 60. Click OK, and let's move on to the next panel. Travel modes, since this is a simple network data set, I could set this up later. Don't need to set it up right now. Patrick will be talking about travel modes later in the presentation as well. Click Next. Driving directions. If I look at the direction settings, it's picked up my length and minutes attributes for driving direction reporting. And it also picked up FE_dir_P, FE_name, FE_type, and FE_dir_S for the street name fields. Click OK. Look at the final panel. We have all the settings that we specified in the network data set. If I could review them, make sure that everything is correct. If anything is not correct, I could go back and change those settings. Click on Finish. It creates my network data set. Click Yes to build, which means that it's going to read each feature and make sure that and create a network element that's connected as appropriate and with all the correct attributes. Click Yes to add it to the map. So let's make sure that we set up this network data set correctly. I'm going to use the Network Identify tool, and I'm going to click on one of these ramp features that I edited. You'll see that the one-way is prohibited in the direction of travel, direction of digitization, and traversable in the opposite direction, which is how I wanted it set up. Its road class value is 3, which indicates that it's a ramp. The length is 0.006 miles, which seems reasonable. And the travel time is about 0.06 minutes, which also seems reasonable for a ramp. If I look in this lower left corner of this dialog, you'll see that it has 2 adjacent junctions and 2 adjacent edges. If I click on the top level, it flashes in the map which edges are connected to this ramp. Notice that's only the 2 ramp features on either end and not any of the ones that are passing underneath. So I've verified that I set up the elevation correctly for this ramp. So I've demonstrated how to take some data, examine the data, add additional fields that I needed, and create the network data set, and then built it, and then clicked on a few features to make sure that the connectivity is set up correctly, as well as the attributes. So now I'm going to hand it back to Patrick, and he could talk about more things that he could do with the network data set.
Thank you, Alan. So let's talk about turns first. Now, I mentioned that lines are just lines on a map, and we've established connectivity, so now the lines are connected on the map, but we need to establish constrictions on the transitions between the edges. I don't think constriction is the right word, but you can either model additional costs onto your network or onto your turn, so this turn always takes an extra 15 seconds, or you can model restrictions, like this turn is not allowed at all, for example. I'll show you how to set up a turn feature. Oh, there's 2 ways to do turn features. One, digitizing in a line, clicking and adding a line. Alan will demonstrate it in a second. And those kind of turn features that are digitized can span multiple edges. So the example here is a turn that goes from street 1 to street 2 to street 3. Maybe I want to say that this always adds an additional 20 seconds because it's an odd intersection. Or we don't want to allow this turn at all because it's illegal. You can digitize that in and it will limit the turn in the way that you specified. But if you try to do this for every intersection, for every turn, at every 4-way intersection, there's 16 different possible turn transitions, including left, right, U-turns, and going straight through an intersection. And so it could be too overwhelming of a task to do that for an entire network. Even a small city would be very difficult. So what you can do is establish global turns. If you want to control, say, I have a big truck, and every time I turn left, it takes me a little bit longer. So let's add 15 seconds to every left turn. So with every left turn in a network, you can add it as a global turn delay, and I'll show you that in just a second. But realize too that if you've digitized a turn in at that intersection, that'll override the global turn delays. Now, if you do want to add a global turn delay, then you need to establish what is a left turn and a right turn and a U-turn and straight by the angles that are on the roads, and you do this with the global turn delay evaluator. And then based on the hierarchy of the roads, I mentioned that some roads are considered more important than others, then you can establish different additional turn costs. So going from a local road onto a highway might take a little bit longer than going from a local road to another local road, for example. Another important part of a network data set could be the signpost data. This is for establishing driving directions. This sign would generate a direction at exit 73B, take ramp US 421 north toward North Wilkesboro. Now, how can the directions engine figure out that those are all the words to put in there? And these are done through a combination of tables and feature classes. There's a feature class set up that can hold each of these little bits of information in fields along it, and a table that identifies what are the features that you transition from one to the other that should trigger this direction being added. And so those are connected by an ID, and each of the features that are involved in this direction maneuver are included in that ID. And Alan will show you this in a second as well. I've mentioned traffic a couple of times, and it can be a very, very important part of a network data set depending on the type of analysis you're doing. Oh, and it didn't go. This is actually a video of travel throughout a network. Let me see if I can reestablish this. And will it go? Okay, it won't. But if the video was moving, what you'd see is that throughout a typical Monday in Los Angeles, a simple 5-stop route can change very dramatically, depending on what time of day you leave. So to establish traffic times, you can use live traffic and historical traffic and predictive traffic, and that can all be included in your network data set. Alan will demonstrate how some of this works. It works through traffic patterns and through a combination of tables. And we'll do that now. I'll turn it back over to Alan, and he'll demonstrate it for you.
All right, thank you, Patrick. We're back in San Francisco again, but this time we're actually using commercial street data, and more specifically, we're actually using the data that's found in the ArcGIS Network Analyst tutorial, exercise 3 to be exact. And this data has turn restrictions, it also has signposts, and it also has historical traffic all set up in here. And I'll show you each of those. So let's start with the turn restrictions. If I turn on the restricted turns layer, you'll see all these features that are digitized. Let's zoom in on an area in downtown. And you can see that there's several that are already digitized in. Simple left turn here. You can zoom in a little closer and you can see some U-turns. So say I wanted to digitize my own turn. What do I need to do? Start editing. Open up the Create Features panel. Click on the feature class I want to edit. Snap it to a street. Snap the other end to a street. And it's created a turn feature. So creating turns is just as simple as creating any other features. Now there's some special logic that's been added to the arc map that allows you to digitize turn features. So if you open up the attribute table, it actually filled in the feature class ID, feature ID, and position for each of the edges I snapped on. So this is the information that the network data set uses to identify which turns refer to which streets. Editing a turn feature is very simple. You could do any other of the operations you do for inserting vertices, moving vertices around, just like any other line feature. Patrick, I'm sorry?
Is that a restriction or a turn?
This is just these are just the turn features. The restrictions are defined in the within the restriction attributes. So if you could say these turns are could be penalized, they could be restricted. That's defined when you set up the restriction attribute. So let's zoom in on a intersection here, and I could show you digitizing a multi-edge turn. You could snap as many vertices as you like to the streets, and you could create the turn that way. Patrick mentioned global turns. If you want to set up global turns, you just open up the network dataset properties, go to the attributes tab, click on a cost attribute that uses travel time, and click on the evaluators tab. click on default evaluators, and normally this would, I think I have a lock enabled because I'm starting editing. Let me correct that. So let's stop editing and save edits. Now I could edit the network data set. Open up the cost attribute, default values tab, and under type for turn, you could bring up the global turn delay evaluator and open up the properties, and this is where you can adjust how long it takes for turns of a certain angle across certain road classes to take. You could also define how wide a left turn is, or left turn or right turn is from a straight or from a reverse. So all this can be set up within the global turn delay evaluator. Okay.
How would you set up a restricted U-turn?
A restricted U-turn, you would use a turn feature as I digitized in.
Yeah, but like
You click it in.
back and forth.
I'm sorry?
How do you click it in?
You would just digitize it in like I did. You just
You're
click.
using two features over here. What if it is an undivided road?
If it's an undivided road, you could actually create a U-turn on itself.
Okay.
I'm glad you asked that question. So if you want to say, I want to say no U-turn from here to here, back on itself, and there you have a U-turn on an undivided road. Okay, so as I mentioned, this network data set contains turns. It also contains signposts. So if I zoom back out to the very beginning and stop editing, let's find a simple route from the southwest corner of the area to the downtown area. And you'll see that it takes the freeways. If I were to generate driving directions, it actually uses the street name for each of these on where to turn. Also, on the freeways, it actually says take ramp on the left and go on US 101 north towards Civic Center Bay Bridge. This is actually derived from the signpost information. So if I open up the network, add signposts to the map, and zoom in on that interchange, which we showed you earlier, and click on the signpost feature that was added here, you'll see that here's the information that you have. Oh. That's the same. So here's US 101 north, going towards the Civic Center and Bay Bridge. This is signpost number 35. So that's how it knows to pull up the signposts. But how does it know which streets that correspond to signpost 35? That's found in the signpost streets table. If I open this up right here and open this up, scroll down to signpost 35, it's a sequence of two edges from edge 11762 to edge 12098. So this information is how it associates the signpost text, which is in the signpost feature class, to the edges in the network. Finally, this network contains historical traffic. Historical traffic is actually in two tables. It's in the daily profiles table and the streets daily profiles table. This first table, if we open it up, contains information hour by hour, in this case every 5 minutes, of how fast it is to travel along the streets. Right now we're looking at the midnight hour, so everything is at 100%. It's basically the free flow speed right now. But if we were to scroll on over to maybe about 7 a.m., 8 a.m., you'll see some streets that are 73% longer, 78% longer, 83, 88% longer, 90% longer. So this is how these multipliers tell you how slow it is for a given class of streets at a certain time of day. So this is how the daily profiles is set up. Now, how is this associated with the streets? That's found in the streets daily profiles table. If I add this to the map and take a look here, you actually see here's the free flow speed and the weekday and weekend speeds, and here are the profile numbers. So if we were to take a look at a street, say this one here, This is profile 35 for Sunday, Monday, Tuesday, Wednesday, Thursday, and Friday. But on Saturday, it uses profile 41. So each day of the week could have a different profile associated with it. And then here's the street ID, feature class ID, feature ID, and position along that associates a certain street with a certain set of profiles for each day of the week. And then the profiles table has the minute-by-minute multipliers for that day. So this is the San Francisco tutorial data within the ArcGIS Network Analyst tutorial, specifically exercise 3 data. So you could take a look at and study carefully on how turns, signposts, and traffic is set up. And maybe you could apply these to the network data set that you guys create. All right, I'm going to turn it over to Patrick, and he's going to talk more about parameters.
Thank you, Alan. I got the thing working. Closing and reopening PowerPoint. And PowerPoint decided this time that it was happy to display this little video. But that's it. Traffic, obviously it changes the route throughout the day depending on the time you leave, especially in downtown Los Angeles, I think. Okay, so we'll cover a few more properties of network data set and then finish up. Let you go on with your day. And one important thing is parameterized attributes. And that sounds complicated, but it's pretty simple. We saw the attributes before: costs, restrictions, descriptors, and hierarchy. A parameterized attribute is an attribute that takes a parameter. It's just a value you pass into the attribute. And this can be used to let the attribute decide whether or not to restrict an element, for example. So is this slope too steep for my truck to travel on? Is this road too thin for my vehicle to get through, or too low? And I'll do a height restriction as an example because that's a very common usage. And the way a height restriction could be set up is by using a descriptor. A descriptor is, for example, the maximum height on this road. Like the maximum height of this road that has a bridge on it is 12 foot 6 inches, and that's a descriptor on that road. It describes how the road works. And you add a parameter. What is the current height of the vehicle that I'm routing for? It might only be 4 feet tall, so it has no problem on the road, but it might be 13 feet tall, very tall road, or has an inflatable panda on the top because you're delivering food. And in that case, you put in the parameters, the height of the vehicle, and then the restriction attribute will compare the description of the road with the parameter you passed it from your analysis and decide whether or not you can travel on that road. So that's how a parameterized attribute works. A descriptor and a parameter work together to make a restriction. There's one special attribute parameter that is on every single restriction, and that's the restriction usage parameter. And you see that bottom restriction usage is set to prohibited. Now that means that if this restriction is on, you cannot travel on this road. But sometimes you want the restriction not to be as hard as prohibiting. It can be a little bit softer. For example, if you don't want to allow travel in a certain area of town, like through traffic prohibited because it's a suburb, but you only want to drive there if you have certain business to do, like a delivery, for example, then you can set it to avoid this area rather than completely prohibit it. And you do that with the restriction usage parameter. Alan mentioned travel modes. I want to mention them briefly. As you see on the right for this network, I think this is a StreetMap Premium network, there can be a lot of restrictions, as many as you want to add to your network. And it's hard to remember sometimes which ones should be turned on and off for which analysis. And so the way you set that up is by bundling them into a travel mode. You establish all of your travel settings, the cost that you're minimizing, your U-turn policy, can my vehicle make U-turns? And all the restrictions that are turned on and off, and some parameters that you might set up. And that way you have it bundled together as one particular travel mode. And you can make multiple travel modes on your network. Walking time, driving time, rural driving time, trucks that are tall or short, however you set it up. So it's a good way to bundle settings. There's a couple of geoprocessing tools, or a few, I guess. Geoprocessing tools available to work with network data sets. I mentioned earlier creating a network from template and creating a template from the network, which are very important. You can also build your network and dissolve your network. Dissolving will optimize larger networks so that there's less edges. So we had an example, someone came up and said the way the roads were digitized were in 200-foot segments. Right? And so that'll end up with a lot of edges and elements. And if you dissolve your network, it will merge those sections together so that only the sections that matter together are combined. You can also make a network data set layer if you're using it within a model or a script, for example. And we'll finish up with support. So if you go to support.esri.com, there are links to help that you can get for Network Analyst. If you haven't used Network Analyst much before, I highly recommend doing the tutorial. And even if you have used it before and haven't done the tutorial, it's a great place to start. It only takes about an hour, and it'll give you a good indication of what the different solvers do and what some of the functionality of network data sets are. And some of the work that Alan did, you'll get to actually go through and work with those tables. So you don't have to remember what every single table does in every single field. Yes, ma'am? How do you access the tutorial? We had a link pulled up that I'll show you. You can find it on the support, but I just Google Network Analyst tutorial, and it'll come up as one of the first hits. And there's a tutorial for ArcMap as well as for Pro. So there's two separate tutorials with a lot of the same information. Alan will pull it up, and then we'll switch over and show you. There's also a couple special things. There's a recorded training seminar that you can get that we have a link to here. As well as some demos and other resources. There's a GeoNet forum for Network Analysts specifically that product engineers answer questions on, as well as some customers who are highly motivated. You found one of them? I'm going to switch over.
Keep talking.
There's also some additional sessions. There's another day of presentations tomorrow, and we still have a geoprocessing session in the morning, which is one that I do, which is really fun. An introduction session if you want to know about some of the capabilities of some of the solvers for Network Analyst. The Python API, web services, and a few other things are still left. Please also visit us down at the Network Analyst Island. So you mentioned you wanted to see information about what you could do in Pro for Network Analyst. You can come down to the island and we'll be happy to give a demonstration for you. We have developers and product engineers there. As you've seen at every presentation, please share your feedback with us. We look at it all and try to incorporate everything you ask us. So anything we forgot to include that you want us to, please put that in there. Anything we did well that you want to note, we appreciate that too. So we'll switch over so you can get a picture of, go ahead, Alan.
All right, so this is the site for where you find the Network Analyst tutorial. The URL is at the top. It's quite long. If you navigate through the ArcMap help, it's under Extensions, Network Analyst, Guidebooks, Network Analyst tutorial. So.
Thank you, Alan. Can you put it back on?
I'm sorry.
Okay, I'll leave this slide up, and I have a couple copies of this if you're interested in going to some more of the Network Analyst presentations. And with that, we'll take some questions. So thank you very much. Yes, ma'am.
So maybe I missed it through the demonstration, but when you were pulling up the tables, how do those tables relate to the feature classes within the network data set?
So the question was, from the tables that we showed, how do they relate to the feature classes in the network data set? For most of the tables that we work with, it'll have two fields, one called feature class ID and one called feature class object ID or source object ID. And the feature class ID is a number that represents the class it's referring to, and the object ID is the object ID that it's referring to in the other table. Can you pull one up, Alan, perhaps? Go to...
Not yet. I'm still getting it up. I'm reopening it again.
Well, Alan pulls it up. And so usually there's basically two fields that identify the other feature classes.
The fields portion of it, I'm just like, so when you're using a function with the network data set, how does it know to go to that table?
Oh, interesting. When you're using a function with the network data set, you mean when it's solving an analysis,
Yes.
for example?
Yes.
So internally, the solvers inspect every element. So you started on an edge. It knows all the restriction attributes for that edge, and that's all been built into it. So the field, you set up the fields, and when you build your network, it creates some internal tables and stuff that the solvers refer to figure out which fields you're talking about. And so if you go make changes to your streets and change values on those fields, the next time you build, it'll build that into your network data set, and then when the solvers are traversing, it can figure out this element, does this restriction apply, and all those things like that. Did that answer your question? If it didn't quite cover it, you can come up afterwards and I can help with your particular use case. Yes, sir?
Those tables were archived historical traffic feeds, right? So why would you how does the Google and you guys get live traffic or report traffic?
So the question was, if I understand correctly, the tables we showed were historical traffic tables with historical traffic patterns, and the question is, how do we get live traffic into the network data sets? So there are, the way we do it with the StreetMap Premium and with our routing services is we use Here's, the company here does live traffic vendor, and you can pull down live traffic from them. There's a tool that'll do it, and then the network data set is aware of where the live traffic is, and it can incorporate it into it. So there's a table, if Alan can show it, that will set up identifiers for the streets compared to the identifiers used in live traffic, and that way when the solver's doing it, it can look it up and figure out what it is. Because like you said, the historical traffic is patterns from the past. So the live traffic is dynamic and has to be updated constantly.
I have an old copy of the tutorial on my machine, but exercise 10, I believe, has the tutorial data that actually shows you setting up the live traffic TMC tables to the San Diego area. And then there's also explanation of how to set up your network data set so that it reads from the live feeds and creating DTF files that the network data set will consume.
The traffic vendors use TMC, which I think stands for Traffic Message Channel, or Traffic Message Code.
Channel, you got it right.
I had it right the first time, darn it. Traffic Message Channel, and those are codes that the vendors use to identify elements, and then we have tables that say which streets have which TMC codes,
and those same TMC codes are found within the traffic feeds, and the traffic feeds are converted to DTF files with those TMC codes.
Yeah. Any further questions? That's it. Thank you very much, and have a good night. I'll see you in the gas line. Thank you.